Okay, I
Let
think
me start. Yeah, now it starts. So, hi, welcome to the second part of this afternoon with in the English track. I know that I'm not as charming as Antonia, who hosted the English track before. Um, However, my guests are charming as usual. We have Sagar here. Sagar will give us some input and yeah, give it a little bit of a personal spin. Actually, it was thanks to OpenEMS that Sagar and myself came in contact. I think it was a few months ago, in order to implement parts of what he is showing us today. Sagar,
absolutely.
you have 80 participants, and as usual, please ask your questions. Use the reaction button, which is somewhere down here. It has a smile on it. If you have any question and feedback, use the chat function. And however, Saga will present, and then we will do a question answer part afterwards to give him the possibility for the flow. So, handing it over, Saga, the stage is yours.
Perfect. Thank you, Thorsten. Uh, Good afternoon, everyone. My name is Sagar. I'm a software developer at FENECON. I have joined the FENECON in 2018 as a working student. I've done my master thesis in the same company. And once I finished my master's, I started working as a full-time employee as well. So this is how I was introduced to the energy storage systems and the energy management system world, which is quite exciting for me. And today I'll be going to present regarding the time-of-use tariffs, which we have implemented a controller based on it in OpenEMS. So I'll be starting with what exactly it is, giving a brief overview of what exactly it is and how it all started in OpenEMS, when exactly and what were the vision, and then the current status in the OpenEMS by explaining what we have implemented and a couple of screenshots of a customer which we have already implemented at site. And we'll conclude with the next steps, what we are planning. Still, there's a lot of things that's going to happen in this controller. So yeah, let's start it. So time of use tariffs, or in general, which is known as dynamic prices. This is a demand response program. So unlike offering flat electricity prices for the consumer, the utilities, they offer dynamic prices which are reflective to the renewable energy available and peak load demand. So before, it was not able to, not possible for the providers to give this price signals. With advent of technology and the smart metering, it is quite easy for the providers to send these price signals way in advance to the customer so that he is well prepared of these prices. And in this way, the consumer can be able to participate in this electricity system. He moreover is part of the electricity system, in fact. So this is beneficial for both consumer and also utilities, because consumer gets the direct monetary benefit by switching the energy consumption from high price hour to the low price hour. And it benefits the utility providers because they get the flexibility on the demand side, and thereby it encourages to increase the renewable energy penetration. So there are various pricing models, various forms of time of use tariffs, in fact. So one is real time pricing, which is in focus for this controller, where the prices change every 15 minutes to 1 hour. This is provided by the utility provider. This is given to the customer way in advance. Similar to that one, we have time of use, where the prices remain same for a certain period of time. So for one example would be, there is a difference in prices for the day and night. And there are many more pricing models as well, like variable peak pricing and the critical peak pricing and stuff. So for this controller, the main focus would be the real time pricing, and the name that has been given to this controller has nothing to do with the pricing model name, which is time of use. This is more related to real time pricing. So where the utility providers provide the prices which changes every 15 minutes. So in this current market scenario, especially when the prices are changing, increasing each and every time, every day, in fact, and there is a huge demand of renewable energy integration in the energy mix, there is a huge gap from the price hours, especially during the peak load time and the normal time. So this offers attractive benefit for the customer, in fact, to shift the energy consumption to low price hours. And especially for the consumers who have the storage system, if they can able to efficiently use the storage system, they can able to generate a great monetary benefits. So the reason why we have focused on developing such a controller which has such a growing demand, in fact. So how it all started in OpenEMS. So we the work actually started in 2018. Like I've already mentioned, I have done my master thesis in this company. I was offered to do my master thesis on this topic, which was quite interesting for me because I have never heard of it before. And during this during my master thesis course, I have analyzed various scientific models which are already existing, from the scheduling logic to the predictions and stuff. So based on all those analyzation, I have generated a report also, which I have submitted in the university. And we have decided to make a separate controller based on our own simplistic assumptions, not to go beyond like a machine learning models and something like that, to be very simple, to be very effective at the customer side on a real world basis. So we have developed, we wanted to develop that controller in OpenEMS and deploy it at customer site and to see a real output, in fact. So we have taken the help of Avatar. Avatar is a company which provides dynamic prices, where the prices change every 1 hour. So they have given a separate key for that, and we were so that we can able to experiment it. And we have developed that controller, and we have deployed it a customer who is in Austria. In fact, we let it run for a couple of months, in fact, and the output was really interesting. And yeah, of course, there is a lot of changes when you compare with the university project. So there's a lot of change happens when we wanted to integrate that controller as a product in this company. So we have done a lot of changes in the edge and the user interface departments from the last few months. In fact, the focus was more on the user interface section, where the customer can see what is happening. For example, for example, to easily let him know what is the controller state, what is the price is looking for, what is the price, the current price information, the history chart. In fact, if he wants to know what exactly happened for the whole day or for the whole night, and the timer, how long the controller actually control the storage system. Um, and we have developed different versions based on it. For example, we have a different controller for the Germany version. Each country has its own limitations, has its own restrictions. So based on those restrictions, we have developed that controller. Initially, we developed for the Austrian version. Later on, when we wanted to put in the Germany market, we had to know some restrictions and we had to change it. A lot of logical side, and we have developed it. The Germany version controller is already out in the public. It is in the OpenEMS develop, in fact, and the Austrian one is in the developed state. And based on the requirement and the demand from the customers, it can be easily deployed. But the focus right now is on the Germany version. And design changes were done since it was done for my university project. The software design was done in such a way that it was a monolithic design. So everything from the retrieving the prices, calculating the predictions, and the schedule logic, everything incorporated in one controller. And later we changed it to individual services. Like like in this one, if you can see the predictions and the prices and the optimized scheduling logic, everything in a one single controller, everything is interrelated to one. So if we have any problem receiving the prices, and the entire controller gets into the error state. So this is what we wanted to avoid it. So, and we changed it to independent services, like we have created a price API, which is a, you can call it as an interface for each and every price provider. Currently we have implemented for these three, currently Tiber and Avatar. So it doesn't matter if the price provider provides different time window prices. For example, currently provides prices every 15 minutes. Avatar provides prices every 1 hour. So it doesn't matter, because the price API, it pre-processes that information and it gives the information for in a 15 minutes window. In a similar way, we have separated the predictions also. There are a couple of prediction models already implemented it, and we get those predictions, and the controller just have to contact these two interfaces to get those prices and the predictions. And the core control logic, I mean the calculation of schedule and controlling the storage system, we have separated in a controller level. So in this way we can be sure that it runs in a fail state condition, and we can be able to know where, if any error happens, we can be able to know where exactly that error happens. And it is quite robust in nature. On a logical side, like I've already mentioned, significant changes have been done on the logical wise from what we have implemented it initially. We had certain restrictions from the Germany market. For example, in Germany, the storage systems which are registered as EES Strom Spiker, they are not allowed to charge from the grid. So the best thing would be to do to use the storage system in such a way that the usable capacity is used efficiently, which means to use only during the high price hours for the consumption. So to calculate it, to differentiate high price hours and the low price hours, it a lot depends on the predictions. Speaking of predictions, we have another problem that predictions are if you consider the predictions, predicting the consumption during the night is quite accurate to a certain level, but it is questionable during the day. And during the day, we need to also take into the consideration of photovoltaic energy into the consideration, which is quite challenging to predict it, since we need to take location, weather, and the specific installation into the consideration. So it is quite it's quite difficult to predict it. So the reason why we stick to run this controller only during the night, and we have differentiated day and the night on the basis of sunset and the sunrise. Anyways, we have the predictions, we get the sunset and sunrise information from the predictions, and we made in such a way that the controller runs exactly at the sunset point, and it calculates the schedule based on the available state of charge and how long it can self-sufficient the consumption. If the storage system is not sufficient for the whole consumption, it targets the certain hours so that we can take it from the grid. I will show a certain screenshot in the next slide. It will be very helpful for you to understand this. And we have made this logic to run every 15 minutes from the sunset point, so that every schedule happens every 15 minutes. So based on the predictions, if we get to know that there is a deviation with the predictions, if the predicted SOC is actually deviated based on what we have expected, it readjusts the controller in such a way that the target hours or the low price hours are more, or it increases or decreases based on the prediction errors. So here is one of the Grafana dashboard. So in the first widget, there is a state of charge. There are a couple of curves. And if you can see that a blue line, which is a predicted SOC, so that would be the SOC behavior if there is no logic has implemented. So if you can see, it drains out at 8 o'clock itself. So this is not we wanted. So if you see the actual SOC curve, so that is the SOC behavior based on the controller which we have implemented. So it maintains in a certain level that the SOC is maintained till the sunrise point, and it is the controller blocks the discharge during certain hours so that it is usable only during the high price hours. For example, here you can see there is a flat line of the SOC. That means the controller actually blocked the discharge from the storage system. That means it's doing nothing, because if you see, these are the high price hours which was calculated by the controller. And if you see in relation with the SOC, that's when the discharge was happening. So we are using this state of charge in certain way that it is usable only during the high price hours. And the number of high price hours increases based on the SOC capacity. And there is a lot of information in this, and we wanted to simplify it just by looking at the dashboard. So the reason why we have implemented states for this controller. So we have implemented 3 states for this. One is standby. Standby is a state where the controller is an idle state. It does nothing. I mean, it's during the day. Like I have mentioned, the controller runs only during the night. So that's the idle state, and the delaying discharge is a cheap price hour, and the allowing discharge is the high price hour. If we apply this states, this is how the dashboard looks like. So it is quite convenient to know what the controller is performing for the whole night. And based on this information, we wanted to make it available for the customer also, to be able to understand what exactly happening with the controller. So there was a lot of discussion regarding user interface, widgets, and what are the information that we need to show to the customer. So this is a live widget we have designed for the controller. So here you can see the mode, which means whether the controller is on or off. On means automatic, and the current price when he is actually looking at the system, what is the current price of that particular hour, and the storage discharge, whether it is allowing the discharge or it is blocking the discharge. If the customer clicks on this live widget, the advanced widget opens up, where the customer can conveniently switch on or switch off the controller. And we are planning to introduce more information on this advanced widget by introducing to show some predictions also. So this is for the next step. And this is for the live widget. For the history widget, we have used a delay discharge timer, which means that if a customer wants to know how long the controller was active, how long the controller was actually controlling the storage system. So 8 hours is a time when the controller was actually controlling the storage system. It was blocking the storage system for 8 hours for the whole night. And if a customer clicks on this widget, he gets a detailed view of all the information. So this is a bar chart. Each bar represents a 15 minutes price values. And like I have mentioned before, the states of the controller, each state has been given a certain color. And this is easily recognized by the user, and he can able to understand very well. So this is one of the customer who was using avatar price provider. Here you can see the idle state mentioned in the blue color. So that means the controller was in an idle state. The controller was active during the nights. So that's represented by the green and the black color. Black color represents the blocking the storage system, because once the storage system is blocked during the night, the customer will be able to consume from the grid for the consumption. And the next steps would be to improve the predictions. Right now, like I mentioned, we are using the predictions only for the predicting the consumption for the night. So we are actually thinking of introducing other methodologies. In fact, we were quite working on few methodologies, in fact, but it was quite challenging to fit into this OSGI framework and to this OpenEMS. So we were planning to use any third-party prediction services, or to use the methodology in a certain cloud provider, and use that as an interface and provide interface and get those values from the cloud. And next, to integrate it with the electric vehicle charging stations and the heat pumps. In the current scenario, current logic, it is just blocking the discharge doesn't work if we are considering the electric vehicles into this account. So we have to work on the price solver. We have to provide a certain window where the storage system can discharge. So we have to provide some boundaries to it, so which involves a lot of linear equations, in fact. So that will be our next step as well. And the third one would be, one use case is that once we have developed or calculated the schedule for the customer, we have to report it back, the schedule, to the price provider as well, so that they can get a better understanding of whether the price they have provided is a cheap price, or whether it is overutilized or underutilized. So if a provider provides such a low price, however, what if many people start using it? It's gonna the price provider gonna run out with this availability. So to make a better plans, so we have to report it back. So there is one such use case, and we are actually planning to integrate it as well. And the main thing which we wanted to do is that to make this controller to run for the whole day instead of just for the night. So that requires better predictions as well. Like I have mentioned, we need a better predictions for predicting photovoltaic energy production, which is quite challenging. And in overall, there are lots of use cases with this dynamic prices. For example, this is just when a provider provides of prices. If the provider provides any reward basis or any other methodologies or any other models, so we can be able to separate that in a specific controller as well. And I believe dynamic pricing is just the beginning. That concludes my presentation. I hope it was interesting, and I'm ready for questions if there are any.
Yeah, thanks, Saga. You already received a question. Peter, if you like, I sent you an invite to stage. However, as previously, I will read the question meanwhile, but hope you're also approving to come on stage. So Peter is coming. Peter, maybe you can quickly bring your question in.
It's actually not a question. It's more a remark. If I remember correctly, Saga, you mentioned that due to German regulations, it would not be allowed to charge a storage system from the grid. And to the best of my knowledge, this is allowed. It's not a problem to charge a storage system from the grid. It's not allowed to discharge it into the grid and ask for the EEG-Vergütung. At the same time, if you charge energy from a grid to a storage system, it becomes gray in a storage system, and you may not ask for the EEG-Vergütung when you discharge from the storage into the grid, but it's not forbidden to charge energy into the storage system.
Okay, interesting. From my understanding, the customer who's connected to who has his PV installation, he has to overfeed in tariff, right? So if he's charging from the grid, it becomes gray electricity because the origin is unknown. So what if he's actually discharging it? So the reason why I heard that the charging is actually not allowed. But yeah, I mean, we need to get full information as well.
You lose the feed-in tariff.
Yes.
That's true, but in any case, it doesn't make too much sense to discharge from a storage system into the grid. So it's, to my understanding, it's not a real problem that you encounter if you take electricity from the grid into the storage system. You would nevertheless not allow the storage system to discharge into the grid. It would not make sense anyway.
Okay.
I have another question, if I may, Thorsten.
Yes, please.
Sure, go ahead.
The third point on your last slide, you intend to report back to the providers the schedules of the customers.
Yes.
That is something you probably are aware of that, but we're talking about very sensitive personal data. So I would make sure that the customer understands and accepts that.
That is true. I mean, that was just a possible use case that we are considering, we are keeping in mind, but we are not pushing it, considering the fact that these are the sensitive information. Yes,
Yeah,
I'm
exactly.
aware of that. Yeah.
Okay, great, thanks.
Okay. Good. Christian, do you like to add a point to it? If so, raise your hand. Thanks, Peter. Unfortunately, Peter, as typical, I have to drop the third person on stage to get space for others. Please don't hesitate. Sagar is here, is happy to answer questions. Sagar, let me add a question actually to you. What is the main challenge that you are facing working together with the different market data APIs? You are currently working with 3 market data APIs.
Yes.
With different tariff. What are the challenges there?
The challenges would be so specific to the market data. So the challenge would be to know whether we have received the prices at one point. What if the server is actually not performing at the source side, and what if we don't receive the market data at time, in fact, because we have to calculate the schedule at a we have to take these predictions and we have to calculate the sunset and sunrise points at a specific time. So if we don't receive this market data at certain points, it would be very it would go in a fail state condition where none of those information are calculated in within this time. So the controller would be, I don't know, I mean, it would not perform, in fact.
Thank you, Sagar. Thank you for being here on stage. I think you are around, your contact details are there. So if there are any further questions, don't hesitate to get in contact with Sagar directly. This is the end of this session. The next one is a little bit of a different network, diving into microgrids, and that's actually what I think, if it comes to dynamic tariffs, the more critical beast. See you in a few seconds, minutes, in the next session, diving into microgrid with OpenEMS. See you in a few seconds.
See you. Thank you.